Leo. Everyone remembers Leo from our first lecture and are glad to have you giving this special lecture today. You're muted, Leo.
Okay, I'm back for another lecture. So I wanted to remind you, well, I want to tell you about P-wave resonant superfluidity. But before I do that, since it's been over a week, I wanted to just remind you what I talked about last time. And so the general subject is superfluidity with bosons, but bosons that can interact resonantly, and therefore form molecules, potentially, with all the caveats that I mentioned last time, that these molecules, quite likely are quite unstable. And so there's a big experimental challenge there to be able to stabilize these systems. But, as a theorist, I have the luxury of assuming that that problem can be solved by brilliant experimentalists and various schemes, like putting things in atoms in optical lattices and then hopefully stabilizing the systems. So let me assume the stability is not an issue and remind you what I talked about last time. So last time I talked about S-wave paired superfluidity, and what I meant by that is I consider bosonic atoms scattering, but they're scattering resonantly rather than in a point-like way. So you're near some Feshbach resonance. And the system I had in mind is rubidium-85. So rubidium-85 scattering and rubidium interacting with rubidium-85. So single species, bosonic species in the trap, and they scatter through Feshbach resonance that do exist. And I showed you evidence of this from early days of work by Clausen and Carl Wyman and Eric Cornell that will explore these resonances. And what I argued theoretically is that we have, in principle, then in a system like this, two types of bosons. We have the atomic bosons, atoms themselves, they can both condense from a normal state. But then we can also have molecules of those bosons. They form molecules which are also bosons, and those guys can both condense from the normal state as you cool. So this is temperature. But then as a function of detuning, there's this quantum phase transition, which will extend to finite temperature. And at zero temperature, it's an Ising quantum phase transition from a molecular superfluid where molecules of these bosons, bosonic molecules, diatomic molecules of these bosons are both condensed, but the atoms have not, to a state where atoms and bosons have both condensed. And so that's a kind of a novel situation, particularly in comparison to fermions, for example, where there's this behavior is just a crossover. When you go from BCS-BC, when you do BCS-BC crossover, you really have a smooth evolution of the wave function that Mirror Parrish discussed from tightly bound molecules of fermions, fermionic atoms, to momentum paired Cooper pairs that are large pairs, if you wish. And so that's a smooth evolution. The novelty here is you have a quantum phase transition for bosonic system. And these two phases are really distinct. They're not just some smoothly connected single wave function, paired wave function that describes them. So then let me just briefly give you some highlights of how we dealt with this system. So here's the Hamiltonian is pretty simple. There's an atomic part where atoms interact with atoms, and that's contained in here. So so atoms can interact with each other. Well, sorry. So there's notation will be slightly different. So there's psi1 are the atoms, and psi2 are the molecules. And heads up, it's going to be, notation is going to change a bit. So here, this is the Hamiltonian for atom, and molecule interaction independently. Then here's the coupling between atom and molecules, which is the not so interesting density coupling. But the key crucial coupling was the Feshbach resonant coupling, which appears here. And it just describes a resonant interconversion of a molecule into two atoms, and the reverse process of two atoms coming together and making a molecule. That's what this Feshbach resonant coupling does for you. And so that's where all the physics is. Then I discussed the physics of S-wave Feshbach resonances. So rather than having featureless like scattering, you have these two channels and you scatter through an intermediate molecular state. But the key point about S-wave scattering in this resonant case is that the intermediate molecular state has an L equals 0 angular momentum. So that's what makes it S-wave scattering. So now I talked about Landau theory. And so the Landau theory is particularly simple when the resonance scattering rather than interaction is not there, just to get a sense. So you have two species of bosons, the atoms and the molecules. Where are the molecules? Here are the molecules. And so the atoms can be interacting with themselves. Molecules can be interacting with themselves, and they're controlled by two corresponding chemical potentials. And the experiment, they're controlled by detuning and magnetic fields and number of particles. But okay, and then there's an interspecies, atom-molecule interaction. And the key point is this Feshbach resonant interaction. If you ignore this Feshbach resonant interaction, then it's very clear that there's two possibilities. There's four phases. Psi1 and Psi2 could be both vanished. That's the normal state. Then there's no condensate neither in atoms nor in molecules, or one of them could condense but not the other, or both could condense. And so you get a phase diagram that looks like this, kind of quite generically. But then the key observation is when alpha is not equal to 0, then you have a more interesting behavior. When alpha is not equal to 0, so you add this Feshbach resonant coupling. Now the key observation is the distinction between this phase and this phase disappears, very much like when you have an external magnetic field on the magnet, the distinction between a paramagnet and a ferromagnet disappears. And so then, again, this stops being a transition, it's just a crossover, and all you have is a normal state. And so instead of four phases, you have three phases. You have the normal state, you have the atomic superfluid state, which has both atoms and molecules both condensed, and you have the molecular superfluid state, which has molecules condensed, but atoms not condensed. Okay. So, and then, I discussed, here's the phase diagram that you should remember in contrast shortly in a few minutes with the P-wave version of this that I will discuss. So again, there's an atomic superfluid of pure atoms. Then there's molecules, both condensed, and these molecules are S-wave molecules, so they have angular momentum L equals 0. And then there's a normal state, and there's a quantumizing transition that we studied quite extensively in this system. Okay, and then there's various details that followed that I discussed. There's lots of novel properties of this, both the phases and phase transitions. And then you can think about it, what happens in the trap. And so now what I want to do is I want to switch gears and show you how different it is from the case of when you have a P-wave Feshbach resonance. So by which I mean you have atoms that can scatter resonantly, but they scatter resonantly through an intermediate diatomic molecular state, which has non-zero angular momentum, namely angular momentum equals 1, which is what makes it P-wave Feshbach resonance. And if you think about it, if you have bosons scattering, the same species of bosons, let's say a rubidium-85 scattering rubidium-85, it will not scatter if it's just a single species. P-wave channel, molecular channel, is odd it's an odd channel under inversion or under parity. And so as a result, you will not have any scattering of a single species of bosons through a P-wave channel in the same way that the fermions with contact interaction won't scatter in the S-wave channel, single species. So what one really needs is two species of bosons in your trap. And luckily, and in fact, that's what inspired this work, we do know that, a system that I will talk about namely rubidium-85 and rubidium-87 are two bosonic isotopes of rubidium, and they have a Feshbach resonance with an angular momentum channel equal to 1. And so that's the system to keep in the back of your mind. But, of course, I'm going to, speak much more sort of theoretically, and, the results I'm going to talk about are much more general. But if you want to have a potential experimental system in mind, that's the rubidium-85 scattering of rubidium-87 system. So P-wave superfluidity, and so now let me go full screen because I won't skip around as much. So again, so you have now two isotopes, or two hyperfine, well, in this case, two isotopes of rubidium, for example, so rubidium-85, rubidium-87, and they can scatter through through a diatomic molecule resonantly, but that diatomic molecule has angular momentum L equals 1, hence this is a P-wave Feshbach resonance. And so the question is, what happens in a system like this? Once I go beyond just two-particle physics, but go to many-body physics, so I have a trap with two species of atoms that have this kind of a Feshbach resonance. And amazingly, the phase diagram that I discussed in the S-wave case, again, it's a detuning versus temperature, is enriched in a very beautiful way. You still have, of course, the normal state, that's the non-condensed state. You still have the molecular superfluid, of course, but as I will discuss, that molecular superfluid is far more interesting because it's a molecular superfluid of P-wave molecules rather than S-wave molecules. So this actually has L equals 1 angular momentum, so it's a spinor condensate, actually. You have an atomic superfluid state, but the cool new thing is there's this large intermediate phase, atomic molecular superfluid, where atoms and molecules both have condensed, but so the molecules have condensed in the same way as they've condensed here, but the atoms have condensed at finite angular momentum. And so that's really summarized in these three bullets here. And this is the kind of the crucial, cool new thing that I'll try to, make intuitive for you. And so again, kind of the cartoon picture is, if without any equations, if you want to have some intuition for it, and I will, hit that point over and over again once we look at some equations, is imagine you have these molecular superfluid that has Bose condensed in here. And now so this has finite angular momentum. So kind of in a cartoonish semi-classical picture, the two species, rubidium-85, rubidium-87 atoms are spinning together, spinning in this molecular while being bound in this molecular superfluid state, but they're resonantly coupled to atoms. And as they resonantly couple to atoms, there's a finite amplitude of admixture of this molecule to a pair of atoms, a blue atom with momentum Q and a red atom with momentum minus Q. And so as a result, what this kind of a molecular condensate at finite angular momentum does is it feeds, it resonantly feeds an atomic condensate of red and blue atoms, but that occurs at finite linear momentum. So whenever this molecule decays, and it can decay through this Feshbach resonance, because it's Feshbach resonantly coupled to create this whole system, this kind of a Feshbach resonant coupling, whatever this molecule decays, it decays in a pair of atoms, but those atoms will appear at equal and opposite linear momentum and Bose condensed. So that's the cool thing.
So Leo, just to make sure,
a finite non-zero momentum condensate, in contrast to conventional bosonic condensates that usually occur at zero momentum. Yes.
So just to make sure I understand the setup correctly, and I think this is what you mean when you said you had a L equal 1 spinor condensate in the molecule, but so you're not picking out one of the projections of the angular momentum, but there are three degenerate angular momentum.
Absolutely.
So experimentally, does that really happen at a P-wave resonance? I would think the magnetic field through spin orbit coupling and things would break this degeneracy.
I think that actually the dipolar interaction is one way that resonance is split. And so, you can repeat all this with additional ingredients, and it gets even more even richer. But so I don't want to do that. And I'll discuss the details of it. But again, the focus will be mostly on this phase as the more novel phase.
Maybe you're going to come to this, but because you're assuming all three of those levels are degenerate, can you still describe it by the usual like P-wave pseudo potential that Anna Maria wrote down, or do you have to generalize this somehow?
You still can, but you need to add one more term, and that's a trivial term that basically splits that degeneracy. It splits the LZ equals to 0 and LZ plus or minus 1 by some dipolar energy. And that's known, and in fact has been measured both in fermionic systems like potassium-40 and in the rubidium-85 on 87 resonance. So the resonance actually split. Okay, and again, so what I wanted to, I should have put this up. This is to be contrasted with this S-wave picture. And sorry for inconvenience of rotating this by 90 degrees, but so tilt your head and compare this phase diagram with this proposed phase diagram for the P wave. It's still detuning temperature phase diagram, but here there are 3 phases, while here there are 4 phases. So the key thing is there's this intermediate phase. And it's novel in that the atoms are condensed at finite linear momentum, at finite moment. So you're macroscopically occupying finite momentum single particle states. That's the cool thing about it. Any questions?
There's a question from Matthew Fry.
Go ahead, Matthew.
So I'm just wondering if, say, you had an L equals 0 bound state causing a resonance in P-wave scattering, this wouldn't happen.
Can you say that again?
So if you had a bound state with L equals 0 that caused a resonance in P-wave scattering, which I know doesn't happen usually, but there are some systems that can happen, would this not happen?
Yeah, I think then I would not have this.
Okay.
That's a good question.
So it really depends.
Yeah.
So it really depends on the character of the bound state as well as the.
Yeah, I'm considering here a system in the continuum and the trap, so there are no really bands. It's really just a continuum model. But one can, in principle, think about optical lattices.
No, I'm asking about the bound state, not band.
Bound.
Oh, bound state. Sorry. Yes. So can you say it again? Sorry, I thought you. Okay. Can you?
It really depends on the character of the bound state, the molecular state, not just how it affects the scattering state. Absolutely,
molecular state it's the driving mechanism for this thing. Absolutely. It's almost like once the molecular state is at this L equals 1. You have that condensate that now can, populate. It can coherently sort of populate this finite momentum atomic condensate, as this cartoon suggests. So, the good news is that, I could really just stop my talk here because, I'll go on a little longer, but, there's no pressure anymore. Because if you guys understand this picture, just even in a cartoonish way, everything else is in the papers that I've cited. And you could go and dig into details if you're interested, if this fascinates you. But, there's really nothing more. The rest is just kind of talking about what these transitions are, what the Goldstone modes are, why does it happen, get a little bit more intuition at the level of equations. But there's really nothing more. Okay? Was there a question?
Can I ask a question?
Yes, please.
Yeah, so before, when the ASF and the AMSF were like the same phase, it was because the molecules always condensed when the atoms condensed.
Great question. Yeah.
So in this ASF, the molecules do not condense anymore?
So here the Q is equal to 0 of the atoms, but here Q is not equal to 0. So you're absolutely right that the crucial thing is these molecules, because Feshbach resonance is at P wave, these guys do not induce atomic condensate at, they don't have to induce an atomic condensate at zero momentum, because they're only resonantly coupled Feshbach resonant coupled to Q not equal to 0 atoms. Okay, they're not coupled to, as you will see, it's as you will see when I write down the Hamiltonian, that will answer your question very clearly mathematically. But the short answer is these guys only resonantly couple. This interaction only couples. It's very much like it's like a Cooper pairing where, you know, this L equals 1 can only couple to Q at minus Q of these atoms, not to Q equals 0 condensate. Okay. Okay, so let me go on. Let me put in some. So first, I already said, what is the motivation? Rubidium 8587 does have a Feshbach resonance. Here's the data for it. Maybe this is not dated. Maybe these it's old enough that I've forgotten. No, this is actually data from Carl Wyman's group, Scott Papp and Pino. Here's what happens if you just have rubidium 85. You have these red curve of, you know, that measures whether you have a resonance or not, and instead you see that there's a P wave resonance. And actually, I've forgotten whether this is the S wave resonance or whether this is what Caden asked me about, whether this is the other projection, resonance of the other projection. I suspect this is the dipolar splitting. And in fact, in this plot here, here's how the two sub, you know, LZ equals to 0 and LZ plus or minus 1 are split through the resonance. These flat curves is how the binding energy behaves as a function of the magnetic field. Again, from that same paper. Okay, and then, you know, so again, so just briefly, and just to define our terms, so it's very similar picture. We have a closed channel, molecular channel, open channel of atoms. There's two types of atoms. They scatter in the closed P wave molecule channel. You tune the magnetic field to tune one channel relative to the other, and when one is near the, you know, near the zero energy threshold, then they interact resonantly, and there's a strong hybridization between them, and now you can convert atoms into molecules, pairs of atoms and molecules. The key new thing at finite angular momentum is that there's a centrifugal barrier that you heard so much about, and so as a result, at least at a two-particle level, the resonance is far sharper than in the S-wave case. I kind of don't want to get into that too much, but just say a few more words about this. So mathematically, the molecular superfluid state or molecular bosonic operator is now a triplet. So you can think of it as a phi x, you know, to create a molecule, you create a phi x dagger, phi y dagger, and phi z dagger. And of course, linear combination of this, for example, phi x plus I phi y plus or minus phi y creates the LZ, definite LZ angular momentum molecule. But that's one way. This is kind of a Cartesian way, coordinate way of describing the triplet of the molecular state here. Okay, and that's going to be important. So the Hamiltonian at two-particle level is here's the kinetic energy of two types of atoms, the rubidium 85, rubidium 87, or blue and green. Here's the molecular guys. That's the P wave molecule. Notice it has twice the mass, approximately, but it's not really twice. It's really in the rubidium 85, 87, it would be sum of the two masses. And then here's the crucial Feshbach resonant coupling. And this, you have to just take my word for it. Here's the coupling, alpha, that's the strength like before. Here's the molecule, it's a vector, so it has to dot into another vector. So the way it dots into another vector is at a psi1, psi2, you destroy two atoms and you create a molecule. But the crucial observation is that for P wave, you know, psi1, psi2 has a gradient here, and that gradient is the vector that dots into this triplet phi molecular operator. And this vector, if you think of it in momentum space, that's the K, you know, it becomes a K, which is the momentum of the psi fields of the atoms. And that's exactly the K that Anna Maria mentioned in her context, where she had K dot K prime. That's the P wave channel that in a single channel model, this is the 2-channel model version of it. And if you want to learn more about it, look at this paper. It's just a general discussion of, S wave and P wave and high angular momentum Feshbach resonances and their applications for fermionic systems. But the two-body physics is the same. So here's one can study two-body physics of this Hamiltonian and predict this behavior of the binding energy or the pole of the scattering amplitude. And so you have a resonance when the energy is positive. Here's the resonance. It has some width, but that width gets narrower and narrower. It gets narrower as e to the 3/2. So when you go to zero energy, it sharpens up. And then on the other side, when you've actually formed the molecular state, it becomes infinitely sharp. Because now it can't decay, within at least this Hamiltonian, it's now a infinitely lived molecular state. And you tune it with this detuning with a magnetic field experimentally, okay? So now let's get some mathematics, some Hamiltonian. So we have two species of bosons in the open channel, psi1 and psi2. Please don't confuse the psi1, psi2 with the psi1 and psi2 of the S-wave case. In the S-wave case, I call psi2 the molecule. Here, there are two atoms, so I have to call them psi1 and psi2. So these are atoms, bosonic atoms. And then there's a molecular guy, that's the P-wave molecule with 3 components. And so now let's discuss these pieces of the Hamiltonian. So the 3 of them are very boring, as before. So here's the just pure atomic BEC. It has 2 types of atoms, psi1 and psi2. Each of them can both condense. Then here's the molecular guy. Since phi is a vector, now it's spinor condensates. It's spinor 1 condensate of molecules. That's the same Hamiltonian that people have used to describe spinor, the actual sort of fundamental spinor condensates. Here, the spin is actually just the orbital angular momentum of the molecule, L = 1. While the sort of the spinor condensates in bosonic systems, non-paired bosonic systems, they have like an intrinsic spin 1 that people have explored extensively. Okay, and so we'll discuss these all individually. Here's the density coupling between molecules and atoms. And then the crucial thing is, again, this Feshbach resonance, where you destroy 2 atoms and you create a molecule and vice versa. And notice, since this is boson and this is odd, K is odd on the inversion, then this has to be 1 and 2 indices have to be antisymmetrized, which is why there's this, the full thing that I wrote down here. Okay, that's the reverse of what happens for fermions. For fermions, you can have a single species of fermions because fermions are antisymmetric. And so in the P wave channel, you can have a 1-1. So it's like they're symmetrized. So now let's talk about Landau theory so we can get some intuition. So let's ignore all the kinetic energy terms and just look at mean field theory, okay? And I assure you, we've gone long, we really understand this well beyond mean field theory. Take this as a cartoon or first cut at the problem, okay? So here's the molecular state, molecular sector. Here's the atomic sector. And here's the Feshbach resonance. So, clearly then phis could condense, psis could condense, both could condense. Notice, by the way, that, if psi, the condensate, psi condensate at finite Q is proportional to Q. And actually that gets back to Grace's question. When Q equals to 0, there's no coupling. That's just by assumption that we're looking at P-wave Feshbach resonance. So then, as Grace has asked, correctly asked, now if I have phi condensed, it's not going to induce automatically, I should say, if psi is condensed at Q = 0, it's not going to automatically induce molecules because Q is equals to 0. So there's some conservation laws. The total number of atoms species 1 plus molecules and total number of species of atoms 2 plus molecules is conserved. So there's really 2 U1 conservations It's like U1 cross U1. And so there's a effective chemical potential for molecules, which is a sum of chemical potential of the two species minus the detuning that you're tuning with the magnetic field. So now, how about we look at the simplest possible regime, or one of the two simplest possible regimes? We make the detuning really negative. So when you make detuning very negative, you make chemical potential very positive. So if the detuning is negative, you make chemical potential of molecules positive, and you make so you make molecular chemical potential positive. So that means molecules really want to Bose condense, and you can track it through. Atoms are now gapped in this regime. So this is very far to the left of negative detuning part of the phase diagram. Okay. So if you do that, then I can just cross off, as I did in this slide. I just cross all this off. I don't care about this. It's because psi's have no chance to condense because their chemical potential will be negative. And so they will now want to condense. They are gapped in this state. Okay, so I just throw this out and I focus on the red boxed equation. So let me get rid of the, oops. Let me get rid of the, okay, so now what happens? Well, it's very simple. It's what people have studied for ages early on. Oops. I guess I'm missing a figure, so let's see. Oh, right. So, yeah, so molecular chemical is positive, so phi will condense, as you can see here. So it's a standard Mexican half potential. The only non-standard thing about it is phi is a complex vector as opposed to complex scalar. So this phi-4 theory is actually a little bit more complicated. It has two quartic terms, G1 and G2. So I can either dot phi into phi complex conjugate and then square it. That's U1 and rotationally invariant. Or I can dot phi into phi and then complex conjugate squared. So there's really two parameters. And so the one that determines what happens is just G2. If G2 is positive, you get one kind of a behavior of a molecular condensate. If G2 is negative, you get another kind of behavior. But again, so I have a detuning nu, and I'm way over here. So I'm far away from anything but the molecular condensate. But I'm just telling you there are two types of molecular condensates that can happen depending on the sign of G2. And that's something that depends on the system, and experimentalists have to measure it and tell me what that G2 is. So I'm telling you what can happen in the two possibilities. So one possibility, and that's not surprising. One possibility is if G2 is positive, then you can just, by minimizing this free energy, this mean field free energy, lambda free energy, you can convince yourself that phi likes to condense into has this form. The constant has this form. It's a sum of two real, it's a complex function, but it's a sum of two real vectors, u plus iv. And u and v are perpendicular to each other. That's the form of the condensate. And physically, that just corresponds to molecular condensate with Lz equals to plus or minus 1. That's the preferred over, that's called the ferromagnetic spinor condensate. There's an alternative one, which is physically distinct, which is Lz equals to 0 condensate. And that one, phi is just a real three-dimensional vector, rather than a sum, complex sum of two real vectors. So here you have a u and a v. So you can kind of think of this as the orthonormal triad of u and v. And this one, you can just think of single vector, u. Okay, so like if you want a cartoon version of that. And this has been explored extensively, so I don't want to dwell on it. It just goes over from spinor 1 condensate that people explored in the, fundamental boson spinor condensate, where spin is really spin as opposed to angular momentum. And, you can study the spectra. In this case, there's a quadratic ferromagnetic mode, which goes as q squared. And here there are three modes, which are all linear. Okay, well, here you have q squared and q. And the key point is the red curve is the gapped mode for atoms. Atoms are gapped. Okay. So now let's go to the other easy limit. That's now go to positive detuning, where now atoms want to both condense and molecules are gapped. Well, so what do I mean by molecules are gapped? Their chemical potential is negative. So I want to have a vacuum of molecules, but I have a condensate of atoms. Now, of course, it's the red box that matters. And so I just erase anything that has phi in it, I get rid of. And so then it just reduces to this. And this is just trivial. And, it used to be non-trivial in 1995 when people studied this extensively. People, both Carl Wyman, Eric Cornell, Chris Green studied this extensively experimentally. This is just two-component, non-resonantly coupled bosonic, two bosonic hyperfine states or bosonic species of atoms, and they're not resonantly coupled together. So then, of course, the possibilities are very simple. You can have a normal state, you can have psi1 condensed, psi2 condensed, or both of them condensed. Since they're not resonantly coupled, you can have atomic condensates, 3 types of atomic condensate, depending on what these parameters, lambda 1, 2, and lambda 1 and lambda 2 are. Okay, again, I don't want to dwell on that. And you can study the spectra, and people have studied this. Esri and Chris Green have studied it as far back as 1997. Any questions about this? So these are the simple limits that you can, just convince yourself, look, if I'm far from the resonance, this is all that happens. Either atoms and there are 2 species of atoms, so either atom, you have an atomic condensate of 3 different potential types, or you have molecules, but molecules have an angular momentum 1, so then there's 2 types of molecular condensates possible depending on the parameters. But so now that's looking between. So naively you would say, okay, maybe you go directly from this atomic condensate to molecular condensate, and that's the end of it. And what I want to convince you now is there's something in between. Okay, so, and the best way and that's going to happen between some detuning new critical 1 to new critical 2. So imagine and the best way to kind of think about this is to start with a molecular condensate state, meaning let's start with this state. Let's start with this state, and we start over here, and we start moving over and increasing detuning, and ask what happens. Well, look at this Hamiltonian here. This is, again, mean field Hamiltonian. So what you should imagine is the phi is well condensed. So phi's are just C numbers. They're just condensates. So they're just complex number, and it's fixed. Either it's fixed to be U plus IV, or it's fixed to just to be a real vector. Okay. So now I want to know what happens to the psi in the presence of this boxed resonant interaction when phi is condensed. There's a question. Could U plus IV case be considered as a bosonic analog of P plus IP? Exactly. That's exactly right. So there's a PX, you can have a PX P wave superconductor, or you could have a PX plus IPY or PX minus IPY. PX plus or minus IPY is LZ equals to 0, P wave superconductor, and LX equals to 0, or any of them, LZ equals to 0, doesn't really matter, is the LZ equals to 0 angular momentum projection P wave superconductor. It's exactly right. This molecule is like the Cooper pair, is the bosonic analog of a Cooper pair when you think about fermionic case. Okay.
So there was a follow-up to that. Is there an analog of the Majorana fermion for the bosons or other non-abelian?
I don't know the answer to that. I haven't thought about it. That's a good question. So, okay, so let's try to convince you that there's something interesting going on from this state. Well, so phi is condensed. So this thing I don't care about anymore. It's condensed, it's just some number. So really I'm looking at these 2 terms. And that's look in the regime. We already know what happens if mu is positive. If the atomic mu was positive, then of course atoms condense at 0 momentum. It costs energy to condense at finite momentum. Here's the kinetic energy. Why do you condense at 0 momentum normally? Because there's this Q squared that's sitting there. So why would you want to be at non-zero Q? But the key observation is that, so you would never condense at 0 Q, because by assumption, we're in this intermediate regime, which is below mu nu C2, where atoms, and so in this regime, by themselves, atoms in 0 momentum would have a negative chemical potential just by assumption. So what pushes them over the top? What pushes them over the top is this. And I'm going to explain that in more detail, but the key point is there's a Q involved in here. Notice again, if Q was 0, you would not condense because this mu is negative by assumption. Okay. So that's just try to think about this again. So this is what we have. Here's our kinetic energy of, let's ignore everything but the kinetic energy of atoms and their Feshbach resonant coupling. There's nothing else in that regime that matters. This is what's going to determine if some instability occurs. And if you think about it, if you squint your eyes and forget the difference between, just as a first cut through it, if you forget the difference between psi and psi star, just think about this. This is quadratic in psi, and this is quadratic in psi. So now there's a Q squared here that says, hey, I want to condense at 0 momentum. While this guy is linear in Q. Remember, phi is just a constant. So then what's the compromise here? I clearly can gain energy by condensing a non-zero Q. Because whenever you have think of Q as a spring, like if you have a spring 1/2 kx squared, and you add a spring F times X, spring, no matter how stiff the spring is, it would always be displaced. So the Q will, the best Q you can do is always going to be non-zero, and it's going to be compromised between this linear term and this quadratic term. So the condensate, the atoms can condense or gain or lower their energy by by condensing a non-zero Q, which costs kinetic energy, but then you can make up that energy by through Feshbach resonant hybridization energy. And so here's some more words about it. You more mathematically said, you diagonalize this Hamiltonian, and when you diagonalize it, your eigenmodes are really, your condensate is a linear combination of psi Q1 and psi minus Q2. That's what the psi plus and psi minus are. If you actually did this diagonalization, you would get mu plus and mu minus. One would be lower than mu1, and one would be higher than mu1. And so that means you can, the one that's lower allows the lower one, this mode, to Bose condense. But it will Bose condense at finite momentum because it's taking advantage of this term. And so, and that's the atomic molecular superfluid. It has molecules in it. It has the phi's in it, but it has atoms that are condensing at non-zero momentum. And again, the physics is just a competition between the kinetic energy cost of condensing a non-zero momentum and the resonant energy, which comes from here, which goes linearly with Q. And so if you just optimize this, minimize it over Q, you just set them equal to each other, the optimum Q is just literally a solution to this green equation. And it's given here. Notice it's proportional to alpha, it's proportional to the mass, if I cross multiply, and it's proportional to phi, which is the molecular condensate, which is a square root of the density of molecular condensate. So, you can plot that Q as a function of detuning. It's 0 over here. And then, it starts out at non-zero value. And then as the molecular condensate becomes less and less favorable, Q, this is decreasing, the Q is also decreasing as a square root. And at some point, that Q will go to 0, and you'll get a conventional atomic superfluid at Q equals to 0. While here, Q is non-zero. And that's your atomic molecular superfluid at non-zero Q of atoms. Does that make sense? And so now here's the phase diagram. Here's the molecular superfluid at large negative detuning. It's either this one or that one, depending on whether G is positive or negative. This is the P wave LZ equals to 1 or plus or minus 1, or LZ equals to 0, which is this, it has this character. And somebody said this is like P plus IP. That's exactly right. So this is what we discussed. Over here, you have the atomic superfluid of 1, 2, or 1, 2 variety. These are at Q equals to 0. And now the intermediate guy is, at least now we kind of ascertained it, and it looks like this. You still have this molecular condensate, one or the other. And then atoms will condense, but now, so yeah, you still have this molecular condensate, one or the other, but now atoms can condense, psi plus combination will condense. And in terms of the picture, when psi plus condenses, it likes to condense, when the G2 is positive, the atomic condensate, it's now a finite momentum condensate, and one can demonstrate that its Q, which is a vector in real space, orients perpendicularly, it orients in the plane perpendicular to the angular momentum of the molecular condensate. Okay, so there's still this rotational invariance, uniaxial rotational invariance around L, because anywhere in this plane, Q can point anywhere in that plane. It has the same energy. So that's a Goldstone mode. Alternatively, if the molecular condensate is LZ equals to 0, then when psi plus condenses, when atoms condense at finite momentum, they like to align their Q with the L axis of the molecules, of the molecular condensate, as illustrated in this picture. So as you can see here now, there's no more Goldstone mode. That's energetically, they're locked together energetically. So there'll be an extra Goldstone mode here as compared to here. Well, extra softness. So, but in terms of mathematics, here's the Hamiltonian I talked about. Here's the kinetic energy, K squared. Here's K squared. It's like a Bogoliubov Hamiltonian. And here's the resonant coupling. That's linear in K. So instead of actually doing what I said before, where you just set them equal to each other and you say, squint your eyes and ignore the stars and say this equals to that and balance them to get this Q, in reality, what you really need to do is you need to diagonalize this 2x2 Hamiltonian, Bogoliubov Hamiltonian. When you diagonalize it, you get, here's your spectrum. And so that spectrum indeed has a non-zero, if you minimize it, it has non-zero K. And the way it looks is if you plot it, you start out with a, here's the molecular modes, one linear and one quadratic, Q squared. That's the ferromagnetic one. That's for G2 positive, G2 positive. And the atoms are gapped. So I'm sitting right here. The atoms don't want to both condense. But now I start moving over to here. So what happens? Well, this guy is going to now come down and develop a minimum. But because of this resonant coupling, it's going to develop a minimum at finite momentum. And this is how it happens. Here it's still gapped. So then you're still over here. Well, you're still over here. And then eventually it condenses here. And so now psi's, atoms have now condensed. And now you've entered into this thing. Okay. And so this is the phase diagram that I started the talk with. And again, there's two possibilities of how the order parameters behave. I'm not going to dwell on this. For G2 less than 0 and G2 greater than 0, this is the LZ equals to plus or minus 1. And this is LZ equals to 1. And then here, there's only one atomic molecular order parameter, U. And here there's two. There's a U and a V.
So Leo, these are different sorts of orders in the AMSF phase, different sorts of spinor orders that.
That's correct. but there are echoes of already different orders in the molecular superfluid state, depending on whether G2 is positive or negative. That kind of carries over and is slaved to whether you came from this one or this one. And that's controlled by one parameter, which is G2, whether it's positive or negative or positive. Okay, so then it gets a little bit more complicated if you want to now study it in a little bit more detail, but let me summarize. Molecular condensate, the polar one, this is G2 less than 0, looks like this. It's just a single vector with an overall phase like any condensate should have. That's the superfluid phase. Then the psi's are really a spinner condensate. It's a linear combination of psi1 and psi2 with a q and minus q angular momentum or linear momentum. That's why it forms a cosine combination. And so that's what it looks like in terms of a picture, but this is actually the structure of the atomic condensate. The structure of molecular condensate is simple. The structure of atomic condensate looks like this. It's a spin 1/2 spinner in the psi1, psi2 space. There's various symmetries one can consider that I won't dwell on. Goldstone modes that remain. Here's the Goldstone mode Hamiltonian that describes the structure of this ASMF polar phase. And then there's a counterpart for the superfluid guy. Now your molecular condensate is U plus IV or N hat plus M hat. It's an orthonormal triad that looks like that. And then the atomic condensate has a different structure. It has a similar structure, but how it's coupling to the molecular condensate is different. And so one has to analyze it. And that controls what the Goldstone mode Lagrangian looks like. And it's slightly more interesting in this case than in the second case than the first case. One can study the phase transition from molecular superfluid. And so here I did it for a polar case to atomic molecular superfluid polar case. And there's an abelian Higgs model of interesting kind that describes it. So, it's a usual condensate, XY-like model for these atoms, but it's happening from the molecular state. But the molecular state has Goldstone modes, in particular L, orientation of the quantization axis of this molecular condensate is a Goldstone mode. So it enters as a gauge field that couples to the atomic condensate that's about to Bose condense. So it's kind of an interesting abelian Higgs model, but it's generalization where the gauge field, that the atoms see a gauge field coming from the fluctuations of the molecular quantization axis of the molecular condensate. So what are the signatures? Okay, well, the signatures are Bragg peaks at finite moment, because the condensate is finite momentum. There are thermodynamic singularities. You can detect it spectroscopically in Bragg spectroscopy because there's a condensation of finite momentum. There's novel vortices and dislocations in this state. And then let me just conclude with what happens in the trap. And it's kind of very similar to what I did for the S-wave case. Within LDA, you basically replace it. It's a good approximation. You replace the atomic chemical potential by a position-dependent chemical potential, effective chemical potential, where the position comes from the trap potential. And so now you have these three. This is the phase diagram in terms of chemical potentials. So now if you start here, you start with molecular condensate. So you have no atoms in your trap, and you only have everything is a molecular condensate, spinner condensate, as you go out radially like that. Okay. But if you start here, you start in the center, you have atomic condensate, which is at finite momentum, which is why it oscillates. This is idealization. You would see, it's subject to the same caveats that Randy Hewlett talked about of detecting FFLO states that he talked about, except this is a bosonic version of it, and physics is different here. But you would see these fringes in an ideal case, or this density wave, atomic density wave, and the molecular condensate would follow it. On the other hand, if you start here, then you would have no condensate. You'd have a zero momentum condensate. That's the blue guy, atomic condensate. No molecular condensate. Then when you cross this point, you'll get the molecular and atomic condensate, but the atomic condensate would be at finite momentum, and then finally have nothing. Or if you're purely in here, you start here, then you only have atomic superfluid, and that atomic superfluid has no molecular component, and there's and it's at zero momentum. So with that, let me just flash up the summary for you, and thank you for your attention. Ask for questions.
Thanks, Leo. Yeah, questions? So I guess I have one sort of general question, which is, so it's great that you have all these symmetry breaking orders. On the other hand, so just having a bunch of symmetry breaking orders is something we've played with in physics for a long time. So do you think that there's something really special about this system's variety of symmetry breaking orders, that it's actually quantum fluctuating in these complex orders or something like that? Or
not really. I mean, there's if I'm really maybe a little bit self-deprecating or a little bit, fully honest, let's say, these are really, if you have something that you can describe with conventional Landau theory, these are conventional phases. They're not some quantum spin liquids or topological phases of matter or anything like that, with some caveat, which I'll elaborate on. But, these are conventional phases of matter in the sense of ultimately, they're unusual bosonic orders, and that's it. So there's really nothing so exotic about them. However, we know about gauge theories, and, you go to here, maybe let me jump out, and, you go to here, and you have a state like this. You have a state like this with this kind of a Lagrangian. Then then quantum fluctuations in this kind of a state do become quite strong. And so then you can get something like a Lodinger liquid-like behavior in the higher dimensional system. So it's still not a topological order, but it's topological maybe in the sense of having quasi long-range order or something like this, and not a fully long-range order as you would in a conventional superfluid, because it has this softer energetics than conventional XY model.
Great. So time is getting pretty late, but any quick question before we pause for the next talk?
Let me just oops.
Did you want to add something, Leo? I'll put that.
No, just patiently waiting if people have any questions.
So if not, I think this is a good place to stop. And so I noticed that Alexei is here. So thanks again, Leo. Our next speaker, Alexei Gorshkov, is here, but did we wanted to take a 5 or 10 minute break so everyone can catch their breath. Did we want to reconvene